Hi everyone. I'm commuting to class right now, and I thought, if I'm going to spend all this time commuting, might as well do something somewhat productive with it. I, was thinking of maybe taking the bus this quarter so I can do more of my readings, but, the bus stop is about a mile from my place. So I was thinking of taking the bike to the bus stop, but my tire's flat, so I just have to wake up earlier next time. But for now, if I'm going to be driving, might as well do something productive with my time. So what I'm going to do is I'll talk about computer science because I think it's very fun and I think it's something worth talking about. So yeah, that's it. You don't care about my background, so I'm not going to talk about it. But I'm going to talk a little bit about computer organization, which I think would correspond to maybe the third class in a lot of undergraduate computer science curriculums at UCLA at CS33. I think this is one of the coolest classes that a lot of schools offer because it really dives into the mechanisms of how a computer works under the hood. And I think that's really fun. That's when it stops becoming magic and starts becoming something tractable, something that you can actually figure, if I was in the 50s and I had $1 million and I was very smart, I could have done this myself. It's not witchcraft. So I think to begin with, it's cool to talk about like what is a computer, like our definitions. And I remember when I was in elementary school, you'd say, what's a computer? And I would think, it's a big old thing, a big old CRT, big old screen right there, that monitor. My concept of what the computing device was the screen, because that's how you interact with it, which I think is really cool. I mean, obviously it was wrong. The classic answer is like, no, it's actually the box that you put the discs in. That's the actual computer. The screen is just a monitor, right? But I think it's kind of cool to think as a kid, and a lot of people still, their primary understanding of these computing devices is the human interface, which I think is a very powerful mindset, to think that, people, when they interact with a phone, they interact with a computer or whatever, they interact with ChatGPT, their primary concept of the being of it is how they interact with it, which makes total sense, right? Anyways, that's a tangent. But I was wrong. The thing that does the computation, the computing, the calculation is the little box. Hardly anyone has desktop computers anymore these days, unless you're like a gamer. So you have like your laptops, your phones, but also you have computers elsewhere. Like a calculator is just a really dumb computer. Not dumb, but it has limited subset of actions that it can do. My car here has a couple of computers. It has the ABS system. Computers can do a lot of really cool things. I think the fundamental thing is that they are machines that can take instructions, execute those instructions, and maybe store and process information. That's just what I think of when I think of a computer. And you think, what kind of information or instructions are you processing on your, 18-year-old car? Like, it's not smart, right? But, the ABS system, that's what prevented me from skidding out on the freeway on-ramp about a year ago. I lost traction. It was after the rain on that curvy on-ramp, and immediately the brakes started going, and that was a result of a computer. The computer was taking in information and was following some instructions. The engineers in Japan said, hey, if you find that the car is moving faster than the tires, or that the speed of the tires are spinning is not matching up with like the actual movement of the car, let off on the brakes because you're probably skidding, So those are instructions, and the action that the computer takes in the real life is to let off on the brakes, save my life. Really cool. other things you can tell it to do. Add 1 plus 1, or now we have AI and large language models taking some human input or environmental input and respond with something that we would find useful. So yeah, it's computers, right? Why do we care? I don't know. I think this is like the next step of the Industrial Revolution, where we first made machines to make labor easier. We built these plows so that we didn't have to, we built these plows so we didn't have to spend so much labor digging holes manually. And later on, we build cars so we don't have to spend so much labor moving around. Although people might have mixed opinions whether or not that was ultimately good or bad for an urban environment, but I digress. It used to. The idea is that hopefully it's making the quality of life better, right? That hopefully we are able to have more leisure time. I'm not sure that's true, but I think it's a good ideal. But the computers right now, there's some decent automation with farming, but right now the computers are, oops, I'm blocking the intersection. Damn. But now the computers are, mostly automating information, decision making, things that, or calculations even, things that would have taken a lot of people a lot of time and energy to do. Like 150 years ago, 200 years ago, I mean, we already had really cool artillery that we were using to blow each other up in the Civil War. And it used to be that people had to manually write by hand. There's a lot of geometry, a lot of math that goes into like blowing things up from far away. People they didn't have time to do the math on the fly in the field unless like maybe you're really smart, but people used to make these handbooks, and they still actually make these handbooks, I think. I was looking at like an army artillery manual, but they made these handbooks with directions and guides and inputs and outputs of, if you want to hit a target this far away, move your gun, move your missile to this, not missile, but cannon, to this particular position. But those inputs and outputs all required a bunch of math, and people used to have to do that manually. They used to have like dozens and dozens of people in, in like little offices in New York or somewhere, writing out doing these calculations, doing this trigonometry, this Pythagorean theorem and all this stuff, sine and cosine, to be able to fill out these books for artillery tables so you can blow things up. The fact is that this calculation was very important for this wartime effort. But it's very expensive to go pay a lot of people who know how to do math. A lot of those people doing math could probably make a lot of money being business folks, or doing other things that you could get money doing math in the 1800s. So it's expensive. And I'm not sure if this is true, but I've heard that at one point this was becoming so expensive for the British Empire that they offloaded the math to like school children. And you think, like, what's the deal with that? Like, what do you mean? How can a school child calculate artillery tables? But the thing is, like, a lot of these calculations, you can break them down into like very simple adding and subtracting, just repeated. So that's what those guys did, is that they used all the school kids, practicing their math tables, times tables, to generate these tables. It sounds a bit more skeptical about that now that I hear about that. But basically, the problem is you have errors. So the idea is that we've made machines to, weave like textiles really efficiently by this time, and we've made machines that can pump water from one place to another, or pump water out of a mine to make it so we can mine more coal and destroy the environment. And we've made more machines that can, we've made a printing press. We made a machine that makes it really easy to like create books. That was amazing for information, for crazy impact on politics. Like, the question was, why can't we just make a machine that does this math for us? And so that was the motivation, has always been, there are some things in life that don't directly involve, or maybe they can directly involve touching things in real life, but there are a lot of things in life that involve our understanding of mathematics, about patterns, about finding patterns in the universe, and being able to predict the next pattern or figure out what the pattern should be, getting kind of philosophical with it. And the idea is like, well, why can't we just make a machine to do that? Like, wouldn't that be awesome? Make a machine, some piece of metal or wood or gold or something that can help us find these patterns in the universe. And ultimately, I mean, numbers by themselves can be fun if you're a mathematician, but I mean, they're not that important. The most important thing for these guys in the military is that they're able to use these machines to predict and plan where to launch their bombs. And there's probably more peaceful examples that I can think of. I just can't think of them off the top of my head. I mean, I think navigation's probably a big one. GPS, being able to predict where you're going to go based off your current location, being able to know where you're going to go. I think really these machines, these computers, maybe the high motivation here is that we're trying to gather information that we've learned about the universe, learn more about the universe, use that to predict things about the universe. Sounds kind of hippy-dippy, but, we're using it to predict the weather. We're using it to predict whether or not you're in a Tesla and you're about to crash into someone and the thing like stops you and prevents you from killing yourself. Predict where the traffic's going to be, or which, given, I go on Google Maps and I give my current location, my current state of the universe, predict what would be the fastest way for me to, navigate to class. So, anyways, I guess that's a high level view of like maybe what a computer is, just from a ranting hippie standpoint. So the thing is, going all the way back to the British, this dude named Charles Babbage said, I could do it, bro. I can do it. Easy stuff. A lot of these calculations, I don't think I'm gonna get into the details, or maybe I will. A lot of these calculations that were pretty complicated, x squared plus y to the third plus z to the, actually, maybe not like multivariate like that, but like 32x plus 15x squared plus 97x to the third. Really, really big stuff. Long equations are being used and had to be solved. It's kind of hard, right? But the guy figured out that you can actually turn a lot of these, this kind of comes down to calculus, but you can turn a lot of these expressions into a series of additions. Let me think of it. I can express this without maybe a screen. So, again, this is not that important to the whole concept of computer, but I think the fact that they use this, we call this algorithm, to turn a more complicated problem, one that is not too complicated for like a middle school or high school student to do, to something that an elementary school student can do. And really, computers are really a bunch of elementary school students. All they can do is add and subtract. Maybe they can do like a multiplication or two. But most of them can just add and subtract and do it really fast. It's like a really fast elementary school student doesn't really know too much of the underlying details. So we can turn, like you have an equation y equals 4x. What you can do is you could say, oh, well, if I know for x equals 0, y equals 0, if we have y equals 4x, okay, that's 0, y equals 1, that's 4. We can say for every step we increment by 4. So we don't really need to know what multiplication is, really. We just keep adding 4 to our last answer. 4, x equals 2, y equals 8, 4 plus 4 is 8, and whatnot. But what if we have, y equals x squared? Okay, weird. Okay, well, this is actually kind of hard to visualize without a screen. But the fundamental idea is that you can actually turn x squared into a series of addition. You don't have to worry about multiplication. You know, you have 0 times 0 is 0 for x equals 0. 1 times 1 is 1 for x equals 1. 2 times 2 is 4. But if you actually do 4 minus that 4 minus that 1, you get 3. Right? Let me think. Yeah. 4 minus 1, you get 3. And then 3 minus... You can do... I have to... Let's see. I have to, like, revisualize this if I get access to a screen. But basically, you can turn this y equals x squared into a very simple addition, a set of additions. Kind of cool, right? And then you can just get a bunch of elementary students, school students who don't even know what an exponent is to solve your math for you. So that's theoretically what the British people were doing. And this smart dude named Charles Babbage said, hey, I can make a machine that can do about the same level of math as an elementary school student. It just needs to be able to add, and it needs to be able, it needs to be able to add a lot repeatedly until we say to stop. So pretty cool, right? So he built like one chunk of this machine, and he ran out of money. He went to the queen and said, hey, this works, but I need more money. And I think she gave him a little more money, and he was like, okay, I'm gonna make a thing that not just does the addition, but also does all this other stuff, that it has a grapher, you know, we can solve for the missing variable, all by breaking these tasks down into like the basic addition and subtraction. And then she was like, okay, bro, you already spent all of our money. It's looking kind of questionable here. So he ended up passing away without ever finishing the machine. But that's just like in the 1800s, they were able to make something, basically a scientific calculator in the 1800s. Pretty cool. Well, again, he designed it, but he never built it. But the cool thing about he made it first his differential machine that was like a calculator, but then he made an analytical engine that I believe it had a few more instructions, a few more things you can do to it. I think you could actually program it to complete several different tasks. But he never actually finished writing. He never actually finished building it, because it's hard to build these machines. It's very hard. So at the same time, this polymath, this mathematician, Ada Lovelace, or Lovelace, I don't know how to pronounce her name. She heard about this, and she was writing to Charles Babbage. She said, hey, this is a really cool machine. Can you tell me about like the specifications? And you know, he talked with her about the whole design. And so what she did is she wrote a script, like a script for actors, but a script for this machine, a set of starting parameters for this machine to calculate terms of the Bernoulli series, actually. So she did this all without the machine actually existing yet, which is pretty cool. So that's why people call her the first computer programmer. And now, like, you know, it's pretty awesome. I mean, there's been a lot of challenges with you know, representation, especially from women in the computer science field in the last, you know, maybe 50 years. But I mean, it's always good to see the history there, that women have always been like very, very intricately involved in the development and use of these devices, these new technologies, since the beginning of their history, which is pretty cool. I'm feeling pretty smug that I'm not blocking the intersection, but someone might honk at me. So there you go. The first computer was never actually built. That guy's kind of bold. First computer program was do some math, and But yeah, what's important for me? I think the history, the context is useful because the earliest designs are relatively simple, and they didn't really do very much, but they're, people made them to solve problems. I think the most cool computers are the ones that were built to solve very immediate problems. Fast forward to like World War II era, people start making, up until this time, there have been a lot of machines similar to the Charles differential engine that can do pretty good computations, pretty quickly. Calculators, kind of things that you would find in a cash register. Those are pretty cool. Mechanical, all spinning wheels and dials. But it's not until like we get around to, a cool thing though, maybe before World War II, is, we start having to process a lot of information, like millions of people's worth of information for the first time in human history. Actually, this is kind of a good and a bad context here. One of them, good, or at least better. Let me merge this. Around the Great Depression, the U.S. develops a Social Security Administration to say, hey, we're making basic social welfare, Social Security that people pay into, so that way elderly people can retire, or at least retired people don't have to be homeless and eat like dirt. It's pretty awesome. Let's go New Deal. And the thing is, to track your benefits, to track your payout, well, there's a couple of things. One, you need to start taxing people in a way they haven't been taxed before. You have to start taxing lots and lots and lots and millions of people. And then to give out benefits, your benefits depend on how much money you're making. They depend on, how much money you put in. It's not necessarily like a pension system. A lot of people think it is. Whatever. That's irrelevant. But basically, you have to process a lot of information for millions of people to effectively dole out this new government benefit. But they didn't have Excel spreadsheets back then. And so what happened was that IBM, International Business Machines, they took up the contract and they said, yeah, we can count millions of people and calculate their benefits and do all this stuff if you pay us. And so they built some of the earliest databases and data processing systems. I have a family member who works for the Social Security system, and she was telling me that, when she started 30 years ago, they still had a lot of this really cool old technology. And so, these days we store stuff in the cloud, and your Google Sheets in the cloud are stored on a hard drive or a solid state drive somewhere at a Google data center. And so if you want to calculate your tax benefits on Google Sheets, it'd be kind of silly, but whatever. That's where it'd be stored. It'd be stored on that piece of silicon or a disk or whatever. Those guys, they figured out how to use punch cards, which are not new technology. Again, punch cards were used to make those automatic looms, to design, really fancy. They're things that you can put into this machine, and it would design a really cool, fancy textile for you. Wouldn't design it. You design it by punching the holes, and it would go, and it would appropriately put the colors that you want on that fabric. Anyways, these pieces of card with holes in them store information about each and every person in the Social Security system, and then you can feed these into the machine, and the machine can do all these awesome calculations. Again, another example of you had a real life need to process information. Very complicated process with a lot of people that these machines, these computers were able to make a lot more efficient. If it wasn't for these, Social Security would not work. I do know that, in Prussia in like the 1800s, they did have like an early social security or pension system. I don't know how they did the analytics for it. I imagine it to be quite expensive and less efficient than we have now. I'm a big defender of social security, by the way, because people think, oh, no, government efficiency. Well, they spend less than 0.5% of their like yearly budget on administration, and 99.5% goes back to the people. I imagine that the overhead costs for writing all those by hand would be much, much, much higher if it wasn't for computers that can do a lot of those calculations for you. So that's my soapbox. So anyways, yeah, historical computers, Social Security, Babbage differential engine. Later on, you start talking about the ENIAC and other similar machines. These are what people start to talk about when you start thinking about the first computer, like modern sense of a computer. And these were computers that you could give them instructions and they could think about something and spit out some really cool custom output. The previous computers that, you know, we used for Social Security, calculating benefits, calculating how much to take from your paycheck, those typically had to be custom built. They had to make the switches and wires custom wired up for that specific problem, and you couldn't use that computer to calculate artillery tables. It was a single purpose computer. Like, you know, it's just a machine that does one thing. Which is cool, it's whatever. I mean, it's fine. But wouldn't it be cool if you had a machine that can do a lot of different things, that could calculate your tax benefits and calculate how to like launch bombs? Then you'd have something really powerful. Because again, it's very expensive to build one of these machines, and it'd be so expensive if you had to build a machine for every different thing that you wanted to do. If you had to build a different machine for, had to build a different computer for launching bombs, a different one for, you know, calculating benefits for orphans, to you know, a different one for calculating, predicting the weather, so you can figure out, you know, how much water to buy for your crops, that kind of stuff. So the ENIAC, I don't know too much about the architectural details of this, but basically that's one of the first machines that goes and is like a general purpose machine that you can go and do a lot of different things. And mostly we used it for like super secret military stuff. And this computer was like the size of a room. Pretty freaking cool. You know, later on in the history, the thing is, a lot of these computers, they need to have some switching mechanism in order to do logic. And if I had like access to a screen right now, I would draw out for you how you could solve any problem in the universe using just like switches. Like I mean like a light switch, right? You turn a light on or off. You could solve any problem in the universe if you got a light switch that can control another light switch. We call that a transistor here, but even before they had transistors, the idea of using one source of information to actuate another little pipe, that is very powerful. Let's see. Yeah, okay. So basically, before we had transistors, you had these little things called vacuum tubes. They kind of function similarly. They're just slower and they break and they're crappy, but they're really cool and cyberpunk looking. Basically, what you can do is you can use, you know, one, you know, source of electricity to control another source of electricity. So what you can do is you can say, oh, well, if this electricity wire is on and this electricity wire is on, then what happens is basically, you know how a light switch turns the light on and off? Suppose you had a light switch to control that switch. And so basically the idea is that you have power coming in and power controlling it, and you could say the output of those two is a result of both of that power being on. If both those switches are on, then bada boom, you have it on. And if both those switches are off, well, then it's off. And if only one is on, then what's going to happen is that your result is it's going to only be, the light's going to be off. If you could do that, and then you also had another one that was flipped around where when you turn a switch on, it actually turns the light off. You can use that not and that and to solve any kind of math problem, any kind of logic problem. It's pretty cool, and there's some like different proofs you can do if you go into like I guess it would be like introduction to like digital logic classes. But basically you can use switches to solve these math problems. You use these switches, these on and off states to represent numbers. And the question is, okay, how do you represent a number with just switches? And I feel like this has been talked about a million times, and you don't really have to care if you can hear. There's probably a better explanation than me. But I guess it's like a really basic way to represent numbers with switches. If you have like, you have a million switches. Suppose you want to calculate. Here's an option, right? Suppose you want to calculate how many people are in the United States, and you think there might be like between 0 and 1 billion. What you could do is you could have, one switch for every possible number. It's a billion, or one light, or one, little electrical source for every possible number, and you light the current one that that's the value. But you need 1 billion, lights just to have the possibility of representing your number. It's kind of janky. And alternatively, let me see if I don't want to get squished by this bus. Alternatively, it's really hard to do math with just like, how do you represent addition if you have just these lights or whatever? Okay. Well, suppose you only have maybe 0 or 1 person, right? You could say, oh, if there's no one there, then the light's off. And if there's 1 person there, then the light's on. All right, well, you can represent 0 or 1 people. The thing is, we can only, in this digital logic, we can only represent on or off. We can't really represent intermediate states very easily. If you can do it, it's just very hard. So the question is, with just ons or off, how can we efficiently capture this information, right? And what we do is we have a binary number system. So you think about it, right now we have our decimal number system. And in our decimal number system, which probably happens because we have 10 fingers, we start at 0. We go to, which is, not every culture has 0. Got a shout out to the Mayans. I'm gonna sound like a fake fan, bro. If it was actually the Aztecs, they're gonna kill me. Take my heart out. JK. And so, okay, going back. You have our numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But then you reset back to 0. So 10 is just 1, 0. Every time you basically have this base, you call this base. Every time you get to like a base, something that is 10, 100, 1,000, something that's an exponential of that base, then you have to reset. And what this is really useful because it allows us to represent. Think about it. It allows us to represent big numbers and small numbers, big information and small information, the same number. 10 or 15 represents that for our big term, or 10, we only have 1 of them. For our smaller term, our 1 is we have 5 of them. And we can represent any number with that. But there's no reason why we have to reset at 10 to represent information. if we were aliens with only 2 fingers, that is a classic, alien with 2 fingers, I feel like such a stretch. I feel like it'd be easier for a lot of the people if we actually, you know, use this to represent, maybe used, what is going on here? Is it a crash? What a mess. Oh gosh. Oh, they're okay. Nope, they look okay. Tragic. Yeah, it's, people go really fast on this road. I don't even know if I'm gonna be able to. Oh, we'll see what's up. What was I saying? Oh yeah. It'd be really embarrassing if I I wonder if my tire's flat. I feel a little bumpy. It'd be really embarrassing if my audio was out and I was just talking to myself. But I guess it helps me deal with the thoughts in my void of a brain. Anyways, I'm not gonna do any cuts because I think cuts, I really do appreciate the old style of like didactic computer science videos that are a bit slower, and they require the thinker to, you know, or excuse me, the speaker to think a bit. It's pretty cool. Oh, let's see. I don't even know if I can access the parking from there. This is really. Anyways, after seeing that accident, I forgot what I was going to talk about. Oh yeah, I remember. I think a lot of people go into the analogy of these numerical base systems. They immediately jump from, oh, humans have 10 figures, we use base 10. We count 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then go all the way up to 99, 100. Okay, it's cool, I guess. But I feel like for a lot of people it might be like a really shift. Really fast. People are honking at me, but I don't think I have the right of way. I think these guys are just trying to avoid the, avoid blocking the intersection, which is good. Like, intersection, not blockers, let's unite. I mean, am I right? Although, I guess I could probably take this space if I was aggressive, but again, it's not really it's not my place. My car's fast, but it's not fast enough to justify that. It's not, my car's not that fast. I'll just wait for this red. Let's go. Alright. Anyways, I think this example I keep trying to talk about is, I think it'd be easier to explain to new people computer science. So maybe an alien had 8 fingers. They count from 0, 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. But instead of seeing 8, it would be 1, 0, right? And every time you have a new place, you know you've multiplied that base by another 8. 1, 0 would represent 8 fingers. Now, it gets a little confusing for a lot of people, but, you know, yeah, I think visualizations are really good for these examples. So 1, 0 would represent the number of fingers I have in a hand, and 2 people's worth of fingers would be 2, 0, right? That's 2 people's worth of fingers. For humans is we call it 20, because we have, you know, 10 plus 10. Yeah, it's pretty useful. 2 people worth of humans fingers are 20. 10 people worth of human fingers are 100. Pretty cool. Well, the idea is that if you're an alien with 8 fingers, well, Anu uses numerical system that reset. We call this octal. It's a decimal that reset at at 8 instead of 10. Then you would be able to have this oh, this was a bad idea. Now I'm gonna be late to class, bro. It's okay. Yeah, well, what was I saying? I should just take the bus, but then I would be able to talk to myself. Yeah, 8 aliens with 8 fingers each. That's 64 fingers in decimal notation. But if we use octal notation, use a special number system that reset at 8, they would probably just say, oh, that's equivalent to 100, because 10, that meant 1 alien worth of fingers. 20, that's 2 aliens worth of fingers. All the way up to 100, because they went up to like 70. That's 7 aliens worth of fingers, and reset all the way up to what we would be 8. It would be, see, I don't want to. These jaywalkers, bro. That used to be me. Still is me. Yeah, anyways. The idea is that you can have different number systems, not just decimal, to represent the same value, the same quantity. It's tricky, right? It can be really tricky. I remember how tricky it was for me. Like, I used to cry thinking about this. Like, I'm not even joking. I used to cry. My dad told me, he's like, yeah, bro, you know how you think you're smart, bro? This is how computers work. And then he whipped up like someone with some nerd with his binary, binary watch. And I was crying, like, how could they know what time it is? And he's like, yeah, you think you're smart, huh? Go do your homework. And, but you know what? It's okay, because a lot of the most fascinating and exciting things in life are the ones that don't come easy. The ones that make you think. And I think the most satisfying ones are the ones that break your preconceived notion of these fundamental ideas of numbers and values and all that good shit, man. So anyways, that's why I like computing. That's why I like computer science. Going all the way down, our basic idea is that we can use different number systems to represent the same values. So if we can use a number system based off of 8s, we can use a number system based off of 10s. Why can't we use a number system based off of 2s? Something that we add a new, it used to be that we add a new tens place every time we multiply by 10, 10 to 100 to 1,000. And, the aliens add a new 8s place every time they multiply by 8. What if these aliens only had 2 fingers, right? 0 or 1. Or rather, you can even say 1 and 1, 0. And then what you would be able to say is that, 1, 0 is the amount of fingers that 1 alien has. 2 zeros is the amount of fingers that 2 aliens have. That's the same thing as us humans saying that 2 humans have a total of 20 fingers. It's just that's all fundamentally based off of our numerical system. I don't know why I'm being picky. Oh, is this vet parking? I don't want to get a freaking fine. My normal strategy, sometimes, man, I'm a total weenie for paying for parking, because I know if I was like, I know there's people out here starving for parking, and then they would they'd say, nah, bro, just park out in Westwood, do a little parallel parking out there, street parking, and you're good. But I don't want to deal with that right now. I want to make it to class. Anyways, numerical systems. Bottom line, computers generally use a binary system. They're like aliens with 2 fingers. You can only count from 0 to 1 because that's how you can represent values with just lights on or off, electricity on or off. And yet they can still represent all the same numbers that you and I can represent with our fancy 10, or decimal base 10 system, or those aliens with their base 8 system. There's nothing that stops them. It just requires a slightly different way of doing math and different way of thinking. But also, the way they do math is really not that much different from us, and it's honestly a lot easier. So if you ever end up in a university computing class and you have to start doing some multiplication or addition in binary, it's so satisfying, because you get to be a machine. And I love my favorite times of life when I get to be a machine, because then you don't have to be human anymore. All right, thank you everyone. That was a longer commute than I needed.